Okay, let's dive right into this. Welcome to today's explainer. If you've ever stared at a massive wall of mathematical equations, felt that mild panic attack coming on, and just been totally overwhelmed by the sheer number of moving parts, you are absolutely in the right place. Today we're taking a really fascinating journey into the heart of linear algebra. But actually, scratch that. We're not going to look at this as some dry academic chore. Instead, we're approaching it like a masterclass in puzzle solving. We're going to take messy, complicated systems of equations and learn the exact, elegant moves required to totally untangle them. So here's our roadmap for this explainer. First up, the three-variable problem. Second, introducing augmented matrices. Third, solving example 1. Fourth, solving example 2. And finally, the geometry of intersections. All right, section 1, the three-variable problem. Now, anyone who's taken basic algebra knows the traditional method of substitution, right? It works totally fine for two variables, but the second you add a third, it quickly devolves into the sprawling mess of substitute this into that. It literally just leads to endless arithmetic mistakes and tear-stained graph paper. So how do you solve a puzzle with three unknown moving parts? Well, the trick is to stop looking at equations as an impenetrable wall of math and start viewing them as a game. Think of it like a Rubik's Cube. This puzzle has very specific, allowed moves you can make to shift pieces around. Moving on to section 2, introducing augmented matrices. To play this game effectively, we need a way to strip away the noise and focus purely on the signal. Look at the awesome transformation happening right here. On the left, we've got standard equations packed with x's, y's, and z's. It's visually crowded, right? But on the right, we've dropped those variables entirely and placed just the core numbers into a structured bracket, an augmented matrix. The positions alone tell us which variable they belong to. The first column is x, the second is y, the third is z, and the right side of the vertical line holds our answers. Notice that if we need to adjust an equation, say by multiplying the second equation by 1/2, we simply multiply that entire second row by 1/2 in our matrix. It's clean, it's organized, and it is ready to solve. Section 3. Solving example 1. Let's actually walk through our very first puzzle, frame by frame. So the crucial point is our initial strategy. Our overarching goal here is to get ones diagonally down the matrix from top left to bottom right and zeros everywhere else below them. Right now, check out the middle matrix. We have a 1 in the y column of the second row, but right below it in row 3, there's this stubborn 3. So how do we eliminate it? Easy, by taking -3 times row 2 and adding it straight into row 3. That brilliantly zeroes out that spot, leaving us with a much simpler -11/2 in the z column. We are systematically clearing the board. With that space cleared out, let's look at our new third row. It currently represents -1/2c equals -3/2. Obviously, we want z all by itself. To isolate our target number, we simply multiply that entire third row by -2. Multiplying a whole row perfectly maintains the equation's balance. And just like that, boom, the fractions disappear. We've established a clean, solid 1 in the bottom right corner of our variables. Okay, we have officially stabilized the bottom row. Now comes that deeply satisfying puzzle solver feeling of working upwards to clear out the remaining numbers. Since we know z equals 3, we can literally use our row operations in reverse. By adding -1 times row 2 up into row 1, we start sweeping away the extra numbers above our diagonal ones. We're actively pushing the matrix toward its final, pure state. And here is the winning state. After our upward sweep, look at what remains. We've reached what's called the identity matrix, a perfect diagonal line of ones, with zeros everywhere else in the variable columns. And this brilliantly illustrates perfectly isolated answers. The top row simply reads x equals 1. The second row reads y equals 2. And the third row reads z equals 3. The knot is untangled. Let's give our brains a super quick reset. What were the actual rules of the game we just played? These are known as elementary row operations, and there are only 3 allowed moves. Move 1, you can swap any 2 rows. Move 2, you can multiply an entire row by any non-zero constant. And move 3, you can add a multiple of one row to another row. That's literally the whole shebang. Those 3 simple rules are all you need to conquer any linear system. All right, section 4, solving example 2. Now that we've got our rules locked in, let's test our skills on a slightly more complex starting board. You'll notice we're using x1, x2, and x3 instead of x, y, and z here, but don't worry, the principle is exactly identical. Our first step is translating this into our augmented matrix. And right away, there's a highly strategic move to make. The middle equation starts with a clean 1. So our very first move is a row swap. We pull that equation right up to row 1, because having a 1 in that top left pivot position just makes the rest of our puzzle so much easier. With our top left 1 completely secured, we can execute some swift row operations to clear out the numbers below it. We've got a -3 and a 2 sitting in that first column. So we multiply row 1 by 3 and add it to row 2. Then we multiply row 1 by -2 and add it to row 3. And boom, the entire first column beneath our pivot point is instantly zeroed out. The board is already looking drastically cleaner, right? Now, what's really interesting about this slide is how we force the math to cooperate with our desired structure. Look at the middle column, second row. There's a 2 sitting there, but we need a 1. So we simply multiply that entire second row by the fraction 1/2. It forces a 1 into that perfect middle pivot position. And the second we have it, we use it as a tool. We multiply row 2 by 3 and add it to row 3, cleanly zeroing out the bottom of that column. We're really riding a wave of mathematical momentum now. Moving to the final column, our third row has a 5. We multiply by 1/5 to turn it into our final diagonal 1. And now we begin that deeply satisfying upward sweep all over again. We use that bottom 1 to zero out the numbers sitting above it in column 3. Row 3 plus row 2 cleans up the middle row. 2 times row 3 plus row 1 cleans up the top row. The messiness is just vanishing entirely. And there it is, the final matrix. The messy starting numbers have completely, gracefully collapsed into our clean, unmistakable identity matrix. Reading straight down the right-hand column, we see our final solution isolated perfectly. x1 equals -2, x2 equals 1, and x3 equals 1. By just following the rules of the game without wavering, the puzzle essentially solved itself.
Which brings us to Section 5, Geometry of Intersections.
So we've spent a lot of time manipulating abstract numbers today, but now we really need to pivot to the aha moment. What do these matrices actually mean in the real physical world? We have to recognize that a linear system isn't just some math problem on a page. Each equation actually represents a flat plane existing in 3D space. When we are solving the matrix, we're physically trying to map out exactly where and how these different geometric shapes overlap and intersect in reality. When you solve a linear system, you're determining the actual physical nature of that intersection. And there are 3 possible outcomes here. First, the matrix might reveal there is no solution, meaning the planes are totally parallel and miss each other entirely. 0 points of intersection. Second, exactly like the puzzles we just solved, the matrix might give you one perfectly neat set of coordinates, meaning all the geometric planes cross perfectly at a single pinpoint in space. Or third, the matrix might indicate infinitely many points of intersection, which leaves us with a truly fascinating question to ponder straight from the source text, as it asks us to use parametric equations to describe solution sets with infinitely many solutions. Think about the physical geometry of that for a second. If a system has infinitely many solutions, what does that actually look like for planes overlapping in 3D space? Does it mean the planes are exactly the same? Does it mean they intersect along an endless line, kind of like the spine of a book? I'm going to leave you to visualize those intersecting dimensions. Thank you so much for joining me on this explainer, and definitely keep exploring the amazing geometry behind the numbers.